Let's talk about light. What is light? Is it like fire that glows from hot embers? Or is it more like rain falling down on us all day? Let's take a look at some models that describe the behavior of light. We'll start by considering it like a wave. You can think of it like water. Well, maybe more like this. The main characteristic of a wave is that it experiences interference, or in other words, peaks and troughs. A wave is not constant. Instead, it is variable and fluctuates often. It was James Clerk Maxwell in the 1800s who took a great part in defining the wave-like attributes of light. Through some deep calculations and study into magnetic and electric fields, Maxwell theorized that light was a combined blend of a magnetic and an electric field oscillating together. The fields crossed each other at right angles, as shown in the image, allowing it to move in a specific direction. As he quantified the wave-like characteristics of light, we are more clearly able to explain some of the things we see in day-to-day life, such as these. For example, light as a wave is able to explain light dispersion and diffraction. Since the wave model of light relies on wavelengths and frequencies, this allows us to describe much about vision and the colors we see day by day. However, despite the wave nature of light, there are still mysteries. Consider now a different model. Let's think of it as particles. Thinking of light as a particle seems almost more intuitive. For example, when we shine a light at a glass or mirror, it's easy to recognize its reflective behavior. This is somewhat like a ping pong ball bouncing up and down. Light as a particle is easy to think about, but hard to explain, at least until the photoelectric effect. Led by Albert Einstein, the photoelectric effect involved shining light at specific types of metal. While experimenting, Einstein found that light of certain frequencies could be shined at the metals without end, to no effect. However, using the same metal source, when a different frequency of light was shined, the light would actually remove electrons from the metal, causing a voltage difference in measuring devices. This, however, only occurred when the frequency of light was high enough, independent of the intensity. The photoelectric effect seemed to show that light had some sort of momentum, the same way a ping pong ball or a bowling ball would have momentum. However, to have classical momentum, light would require some sort of mass. But how could light have mass? It certainly doesn't seem to weigh on us or get any heavier throughout the day. In continuing study, Albert Einstein uncovered the reality and application of light's momentum. His investigation of the photoelectric effect yielded him a Nobel Prize in physics. Particles of light have momentum, but it's a different type of momentum. As described in this equation, the momentum of light is Planck's constant divided by the wavelength of the light. As the wavelength of light decreases, meaning higher energy, the momentum increases. We have seen that light has both wave-like characteristics and particle-like features, and so is born the concept of the photon. In short, a photon is a wave-particle light emission, displaying both its wave and particle characteristics. If light exhibits particle-wave duality, we might still wonder, when is it which? Or is it always both? Which characteristics dominate its behavior? Why does it act differently in different settings? Really, it depends on what we are observing and where we are looking. Every day we see things through light, like houses, cars, trees, and even mountains. Most things we see with our eyes measure in feet, meters, and even kilometers. When we look at the size of a photon, we can tell that they are much, much smaller. The electromagnetic spectrum shown here describes possible wavelengths of photon emissions. The light we see makes up only a small portion of those possible photon emissions. The wavelengths we see are not measured in meters, but rather in nanometers, millions of times smaller. In the act of opening a door, light seems to rush in and seems to act fully like a particle or a ray, bouncing around in straight lines, very sharp, nothing like a wave. That is because the minute photons of light are interacting with objects larger than their own wavelengths, as in our regular size world, then the photons will behave as a particle. It is only when light interacts with things around its own wavelength size that we see it begin to act more like a wave. As an example, in a much smaller frame of reference, we could observe that photons traveling through a very small slit, about the same size of its wavelength, will then propagate and act as a wave as they go through this slit, spreading out like ripples in water. In this example, on the other side of the slit, light would interfere and spread out across the space there. But at the end of the day, it is the particle-wave duality of photons that enriches and enhances our human experience. Our daily lives are shaped by things we cannot see. From the plants that we see as we walk around, to the bright blue skies anywhere you are in the world, and even to the warmth we feel as we carry through our days. And that is the value of the photon.